Hey, so fun never ends with planar transformations, and just going to continue looking at a variety of more sort of transformations we can express through a matrix or matrices. And so let's start with this. So we have a point that is rotated, which is related to reflections. If you rotate something, you can also express it as a type of reflection, and so the transformation matrix will be very similar to one we saw earlier, and then translated. Well, first, let's think about the transformation, and 120 degrees clockwise. Let's kind of think what that means. Clockwise, again, about the origin, so that's going this way 120 degrees. However, as we've seen that by convention, when we're working with a rotation, we want to try to stick to a positive angle only. So let's think about the angle instead of being 120 degrees clockwise as being 240 degrees anti-clockwise or counterclockwise. It is the same thing, but we are encouraged to think about it that way. And so that transformation there, regardless what the shape is, can be expressed by this transformation matrix of the cosine of 240 degrees and minus the sine of 240 degrees and positive the sine of 240 degrees and again the cosine of 240 degrees. The structure of this is extremely similar to what we saw for a reflection along some line, because again the two really are related. So this here will tell us, if I then multiply by the point, and the point is -2 on the x and 5 on the y, that there, sorry, I'm reading the wrong part. That's the translation vector. The point is -3 on the x and 4 on the y. And so this will take care of that transformation. I could go on, but I will just also realize that all of these do relate to special angles. And so just because these lead to fairly nice values, this is the same as -1/2 √3/2, -√3/2, and -1/2. Those are all special angles, or related to special angles. All right. That said, to multiply this out, a GDC is quite helpful, and we will then, whatever we get there, we want to add this translation vector, which we've seen in earlier parts of the course. This here just means we're moving 2 to the left and 5 up. And so once we have that first multiplication step done, we just add this vector. At this point, though, use your GDC as much as you want, and we should get to approximately 2.96 and 5.60. That's our image point. And keep in mind, again, this here is just the rotation, and this was the translation. Okay. Again, looking at a combination of transformations here. I have an object that is first rotated pi/3 or 60 degrees anti-clockwise about the origin, and then enlarged with a scale factor of 3, which means all its dimensions, in this case it's 2 dimensions, is 3 times more, 3 times wider, 3 times higher. And I want to describe, though, those two transformations as a single transformation matrix. So first, though, let's realize what we have here. If we're rotating 60 degrees anti-clockwise, that means I can express that as, like before, the cosine of 60 degrees, or pi/3, minus the sine, and so on. And if I just took that and multiplied by some matrix A that represents these vertices, that there would be just the rotation. Okay? However, the idea is after that, we then enlarge everything by a scale factor of 3. So once I would have this figured out, we would then multiply all of that by the enlargement transformation matrix, which is very simple. When you have an enlargement by a scale factor of 3, it's just a diagonal matrix with 3 on the diagonal. And so in this case, it doesn't really matter what A is, so I'll erase it. All that matters is that these two matrices together, multiplied in this order, will represent these two transformations together. And again, similar to the last question, those angles for cosine and sine are all special values, special triangles, special angles, whatever word I'm trying to say. You're probably not listening anyway, so that's okay. And I'll write those values down, although I'm going to go to my calculator anyways, just to speed it up. Okay, so again, this is the enlargement, this is the rotation, and when you multiply those, you get exactly 1.5 on the diagonal, and approximately negative 2.60, and positive 2.60 to 3 significant figures right there. And so keep in mind, this here represents the transformation matrix that accomplishes both these transformations in this order. This one transformation matrix applied to any two-dimensional shape will rotate it 60 degrees anti-clockwise and enlarge it by a scale factor of 3. Right. Lastly, kind of the other way around, I have an original image, this triangle, and then a transformed version of it, what we see with A prime, B prime, but they still share the origin, O. And we want to determine, okay, what's the transformation matrix that created this? Well, the key to this is first to realize that we can't use our matrix multiplication to solve for the transformation matrix like we did in previous questions. And that's because if we think of like T as a transformation matrix times A, for example, equaling A prime, you may, A being, let's say, this point here, and this A being that point, A prime being that point there, I can express those as a matrix. For example, that A would just be 1, 0. Those are the coordinates there, but that's not a square matrix, which means if I want to try to isolate T, and if I wanted to multiply both sides of this by the inverse of A, well, A is not a square matrix. It doesn't, I can't find the inverse of it. So I can still answer this question, I just can't solve directly for T like we've seen in other questions. Okay, so what can we do? Well, let's think about a matrix here where we have some transformation matrix, and I'll just call it A, B, C, D. I know if I multiply, let's focus on point A, which is at 1, 0, or in this case, 1 over 0. I don't know what the transformation matrix is, but I know after I multiply by it, that point ends up right here at A prime, which is at -5, 1, or as a matrix, -5 over 1. And now I can start to look at my matrix multiplication and come up with some equations. For example, if I perform matrix multiplication, I get A times 1 plus B times 0 equals -5. Or just A equals -5. And I could then go C times 1 plus D times 0 equals 1. So C equals 1. That said, I now know half my matrix. If I look at the other, and at that point though, I don't have enough information to go completely on, but I do know half my transformation matrix. And so this was for point A. Let's now do something similar for point B, from here to here. And so this time I know A and C. So I have -5 and 1. I don't know these ones. And I know when I multiply this by point B, which is at 0, 1, it'll end up at B prime, which is at -2 and 3. And same idea. Let's perform some matrix multiplication. -5 times 0 plus B times 1 equals -2, which means B equals -2. And lastly over here, 1 times 0 plus D times 1 is 3, so D equals 3. And notice I now know my entire transformation matrix. So I'll just say T, my transformation matrix, I now know is -5, 1, -2, 3. And that there will perform the transformation to go from here to here. Lastly, the question is, what's the area of, use this to find the area of that triangle. Now, we could find the area of the triangle using some fairly basic geometry, like the Pythagorean theorem and things like that, to find the height and the base and all that. However, if I just look at the small triangle, I can just see this has an area of 1/2. base times height divided by 2. And I can see this is an enlargement, and that's all that really matters. And I can figure out the exact enlargement factor by finding the determinant of this transformation matrix. That was the last of these ideas. The determinant of this transformation matrix, well, basically tells me how much it's been enlarged by. And so the determinant, remember, is in this case -5 times 3 minus -2 times 1. So the determinant of t in this case is -13. And so the absolute value of that, so the absolute value of the determinant, which in this case is +13, that tells me the scale factor. This is my enlargement scale factor, which means the area of this is 13 times more than this. And I just realized I said one thing wrong. I said this is the enlargement scale factor. It's not. It's the scale factor for the area, which is a difference. The area is 13 times more than half. And so that means the area of this triangle here is 13 times a half, or 13 halves. All right. I think I'm going to shut up now.